Good day. Today we'll be studying motion with varying acceleration. Before we begin, I'd like to point out that you should have the following prior knowledge before studying this particular topic. So, if you don't have enough knowledge about the concept of measurements and vectors, likewise with the 1D and 2D motions, as well as the basic skill set in differentiation and integration, you must visit these topics again and go back after you've learned these topics. In kinematics, we've learned that for every motion, we can actually extract the equation of motion. And for one-dimensional motion, we have the following four equations given by Vx equals V0x plus axt, wherein our Vx here is our final velocity and V0x is our initial velocity. Also, the ax is our acceleration, which is actually constant, and t is time. We also have the second equation, which is actually given by x equals x0 plus V0x times time plus 1 half ax t square. We also have x equals x0 plus 1 half times V0x plus Vx times t. And the last one, we have Vx square minus V0x square equals 2ax times x minus x sub 0. The equations of motion discussed earlier are not applicable for systems with varying acceleration. One must identify the explicit form of acceleration first before extracting the equations of motion, which is done by integrating the definition of acceleration and velocity. Now, to solve the equation of motion, we recall the definition of acceleration, denoted by a, which is given by the derivative of the velocity v. We can then rewrite this expression by cross-multiplying and integrating dv and the expression a dt prime with the lower and upper limit of dv given by v sub 0, which is the initial velocity, and v, which is the final velocity, while for dt, the lower limit is given by 0 and the upper limit is given by time, which gives us v minus v sub 0 equals integral of acceleration times dt prime evaluated from 0 to t. This expression is called as the velocity integration. Now, to solve for the position, recall that from the definition of velocity, which is v equals the derivative of x being the position, we can again cross-multiply this expression and integrate to yield x minus x sub 0 equals integral of the expression v0 plus integral of a dt prime times dt double prime. Now we have to take note that the expression here v0 plus integral of a dt prime is just the expression for the velocity. After simplification, the equation that is x minus x sub 0 equals v0t plus double integral of a dt prime dt double prime. This equation is called as the position integration. Now, let's apply the concepts we learned from extracting the equation of motion for systems with varying acceleration. Let's consider the problem which states that Tanjiro moves straightly and attacks the upper rank 4 using the first form of his Hinokami Kagura. At t equals 0, when Tanjiro is moving at 10 meters per second towards the positive x direction, he passes a big tree at x equals 60 meters. His acceleration while attacking is a function of time given by a equals 4 meters per second squared minus 0.20 meters per second cubed times time. The question is, find Tanjiro's velocity and position as a function of time. Now, to solve this problem, we note that we have the following given, wherein it says that at t equals 0, our initial velocity is given by 10 meters per second and the initial position is given by 60 meters. To solve for velocity, recall that we have the expression v minus v0 equals integral of a dt prime, wherein a is given by 4 meter per second squared minus 0.20 meter per second cubed times time. We then substitute the expression for the acceleration and the value of the initial velocity to get 10 meters per second plus 4 meters per second squared times integral of dt prime minus 0.20 meters per second cubed integral of t prime dt prime. Now, by integrating dt prime in the second term, we get 4 meters per second squared times t, while when we integrate t prime dt prime, we get 0.10 meters per second cubed times t squared. So the expression for the velocity is given by 10 meters per second plus 4 meter per second squared times t minus 0.10 meters per second cubed times t squared. This is the expression of the velocity of Tanjiro while attacking the upper rank 4. To solve for Tanjiro's position, recall that the velocity is expressed in terms of the derivative of position with respect to time, wherein if we solve this expression, we get x minus x sub 0 equals integral of velocity times dt prime. Since we obtained already the expression of dt prime earlier, we just substitute it here, which gives us 60 meters plus the integral of the expression 10 meters per second plus 4 meter per second square times t prime minus 0.10 meters per second cube times t prime square dt prime. Now, we distribute dt prime and the integrand sign to yield 60 meters plus 10 meters per second times the integral of dt prime plus 4 meter per second squared times the integral of t prime dt prime minus 0.10 meter per second cube times t prime cube dt prime cube. When we evaluate the integral found in the second term, third term, and fourth term, we get 60 meters plus 10 meters per second times time plus 2 meters per second squared times t squared minus 0.025 meters per second cube times t fourth. This is the expression of Tanjiro's position while attacking the upper rank 4. That ends my presentation. Thank you, and I hope you've learned something from this discussion.